Hi kids, it's Earth Day, so that's kind of cool. It's the 50th anniversary of that, and I already given and recorded an AP physics lecture, and so you guys get the round 2. So this is I really wanted to kind of be here so you could kind of see the room and kind of feel comfortable in that. So this is kind of a philosophical kind of lecture that leads into some big equations. So I really wish you all were here because for any number of reasons. But because this is cool to have interaction in terms of this, because it gets fairly philosophical, and I'd love to be able to like see your faces and see Lauren go, oh, wow, mind blowing, okay? Or today go, oh, I gotta have some tea after this one. I gotta have some tea. I can't handle this without, And Bruce going, okay. And Connor would be going, yeah, okay. Okay, all right. So the first thing we have to do is lay out some groundwork. And don't worry about writing this down. I'm going to email you all of these lecture notes, okay? So don't sit there and worry about writing this down, okay? I'm going to email you all the lecture notes. Don't flip out. So one of the things we got to figure out is this whole definition of spontaneous reactions. Now, we've talked about spontaneous reactions before, okay? Like, for example, the sign of E naught. What does the sign of E naught have to be for it to be a spontaneous reaction? What sign does delta G have to have for it to be a spontaneous reaction? Okay, what does the value of K have to be for the forward reaction to be favored? Okay, and all of those are going to fit together nicely by the time we get done. So, here's the main thing on a spontaneous reaction, is that once you start it, you don't have to provide any excess energy to keep it going. So let's say, I'm not going to do this for any number of reasons, but let's say that I spilled my Dr. Pepper. I know Dr. Pepper is not a sponsor of this lecture, but if I spill my Dr. Pepper, it's going to spill, okay? And I won't have to keep forcing pop out of it. As soon as I knock this thing over, that liquid's going to spread out. So that's a spontaneous reaction. If you look at hydrogen reacting with oxygen when you blow up a hydrogen balloon, okay? Once you get it started, that's a spontaneous reaction. The hydrogen and oxygen are going to react with each other. You've also worked with non-spontaneous reactions where you had to have an input of energy. So if you all remember back when we had the 9-volt battery and we hooked that up and we dipped it into that solution of silver nitrate, and it plated out that silver. So the silver by itself is not going to turn from silver ion into elemental silver, but because it's more stable there. So the other idea that's going to come out of this, and we've talked about this before, is the idea that Mother Nature is a lazy prima donna. Mother Nature is only going to do what is easiest and most stable for Mother Nature to do, okay? So when you look at this getting philosophical in terms of even the universe, and you can think of this idea of entropy, and entropy is a measure of disorder. To a certain extent, you can think of that as like a measure of time, because it'll only go in one direction. So if I spill this pop, again, which I'm not going to, that has a direction, a certain arrow of time, okay, that says, wow, that pop got spilled, that put in motion a certain point in time. I can't reverse that process. I can't reverse time in terms of spontaneity and make that pop go back into the can. I wish I could, okay? Especially if you were a little kid and you had and your superpower was that you could reverse spontaneous reactions, or you could reduce the decrease in entropy. So you could decrease entropy, and you could just say, wow, here's Timmy, he spills his milk, and his superpower is, I got this, Mom, okay? And puts his hand out, and the milk just, flows back into the cup. The cup stands back up. He goes, no worries, Mom, I got you covered. Now, that would be cool, right? But it would violate a couple of laws of physics. And Mother Nature kind of frowns on that, okay? Just saying. So, but what's important is that you can think of spontaneous reactions as being a direction in time. Now, one of the things that we're going to get into that's going to be very vital is that some reactions are spontaneous, but they're only spontaneous at certain temperatures, okay? So if I take, like for example, I've got a chunk of ice, okay? Is melting ice, is ice melting and turning into liquid water a spontaneous reaction? Well, yes and no, okay? So if I'm in a walk-in freezer and it's minus 5 degrees Celsius and I have a chunk of ice, that ice is not going to melt and turn into liquid water, okay? It's not going to. If I'm at 0 degrees, absolute freezing, okay, that's going to be that transition state. It's going to be an equilibrium at that point. But if I am above 0 degrees, let's say that I'm at room temperature, I'm at 20 degrees Celsius, well, that ice is going to melt and that's going to be a spontaneous reaction. Okay, it will spontaneously melt. All I have to do is set it out. I don't have to keep putting in energy into it. Now you can reverse the process too. Is water freezing and turning into ice a spontaneous reaction? It depends. If I'm at room temperature, it's not, okay? I could say, all right, here's the lab we're going to do today, kids. We're going to take, 25 milliliters of water, and we're going to put it in a beaker, and we're going to see if it freezes. And I'm like, well, that'll be fun. Okay, we're just going to sit there looking at it going, do. Nothing's going to happen. But if I take that same water, and we all go into a walk-in freezer, to get really, really cold, then that water's going to freeze. And Brooklyn, in her, solar bling and her, hooded sweatshirt will be going, oh, this working is really, really cold. But at that point, that is going to freeze. That water will freeze because then it becomes a spontaneous reaction. So some reactions, you'll see there's going to be 4 different categories of reactions that we're going to look at. Some reactions are always going to be spontaneous. Okay, they're not temperature dependent. Some reactions are dependent upon low temperatures. Okay, like let's say, for example, if you look at like water freezing, okay, that's dependent upon a low temperature. You can look at other reactions that are dependent upon high temperatures. So in other words, for this reaction to be spontaneous, it has to be above a certain point, okay? Like for example, boiling water, okay? If you're going to boil water and you're going to have it transition from water into steam, it has to be above 100 degrees, okay? If ice is going to melt, it has to be above 0 degrees. So there's some reactions that are spontaneous at high temperatures, some reactions that are spontaneous at low temperatures. Some reactions are always spontaneous. You're also going to see that there are some reactions that are never spontaneous. Okay? They're never going to happen without an outside force. So here's the classic example. You look at, you have 3 main constituents that make up a tree, okay? Carbon, oxygen, and nitrogen, okay? So if I take like a 5-gallon jug that we get water out of, okay, I say, hey, I want to try and make a tree. And I ingest a chunk of charcoal, okay, there's my source of my carbon. I've got some oxygen from the atmosphere, okay, got that. I got some nitrogen from the atmosphere, that's it. So if I take this chunk of coal and some air, oxygen and nitrogen, and no, there are no air molecules. There's oxygen molecules, there's nitrogen molecules, those are the big hitters. But if I take that chunk of coal, which supplies my carbon, and that oxygen and that nitrogen, and I shake that thing up, okay? Excuse me. I shake it and I shake it and I shake it. No matter how long I shake that thing, I am not going to have a twig appear inside that container. It's not going to happen, okay? So that's a situation, no matter what, I'm not going to have a spontaneous reaction take place. So you'll see this, and we'll work out the math on it later. So there's 4 options when you have reactions. Always spontaneous, spontaneous at low temperatures, spontaneous at high temperatures, or they're just not spontaneous at all, okay? So just kind of the big picture we're getting into that. Now, don't confuse a reaction being spontaneous with a reaction happening fast. A lot of times they do, but that isn't always true. If you look at a nail that is going to rust, okay, a nail rusting is a spontaneous reaction, but it doesn't happen quickly, okay? You look at a diamond, okay? A diamond, you know, that's the old advertising line, diamonds are forever, not from a chemistry standpoint. Diamonds are actually, in a spontaneous reaction, are going to turn into graphite, okay, which is what you use to write with. Now, that isn't going to happen overnight. It's a spontaneous reaction, but it takes a very, 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 very long time. So, if you ever get a diamond, or if you're given a diamond, you know, don't look at that and go, it's just going to turn into graphite. Really, what's the point? Can we just go get pizza? I'd rather have that. Okay? No. Okay? Don't worry about it. It's a very, 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 very slow process, but it is spontaneous. Okay. Now, so now we need to look at a little bit of math. Okay? Just a little bit. So, when you look at what's going to happen here, and I'm going to try and, I've been talking for about 20 minutes. We'll see how long I can go and how long I think your attention span will last. Usually I like to talk about an hour for this too, so we'll see how it goes. So, when you look at this idea of probability, and again, Mother Nature basically only does what's most favorable for Mother Nature to happen. So, what we have here is, hold on, let me get this where I can write on it. Here we go. Okay. So we have two different sides of this container, A and B, and we have a passage through these two particles so that they can go in between. So let's say that we have a single gaseous particle, okay? We just have one. So if we want to figure out the positional probability of it being over here in A, okay? Well, you only have a 50-50 shot. It's either going to be in A or it's going to be in B. So the single particle, define that single particle over here in A, is basically you got a 1 in 2 chance. Now, technically it could exist in between, but I just put that there so that you could see that they're connected. The chance, it will never actually exist in that corridor. So don't get technical. You go, well, couldn't it exist in between? No, it's either going to be in A or it's going to be in B. Now, let's say that you have two particles, okay? And let's say that you're going to have a particle here and you can have a particle here. So if you look at that one, then that's still going to be 1 out of 2 because that's how many states we have. And then we're going to square that, and that's going to become 1/4. So you have two particles, okay, A and B. So if you look at what could happen, you could have A and B over here. You could have A and B over here. You could have A here and B here. You could have B here and you could have A here. So those are your 4 possible states of where this thing can be. So you got a 1 in 4 chance of finding it in one of those. So the pattern here is if you go to 3 particles, A, B, and C, then you got 1 over 2 cubed, which would be 1 over 8. So the chances of finding all of those particles, all 3 of those over here on one side, are 1 in 8. So what that would mean is that this side over here would have all 3, and there would be no particles over here. This would be a vacuum. Or you would have all 3 particles over here, and this would be a vacuum. That's only a 1 in 8 shot of that happening. Now, imagine that you have a mole of gaseous particles in here, okay? So if you have a mole of gaseous particles in here, then imagine that you're going to take 1 over 2 and you're going to raise that to the 6.02 times 10 to the 23rd power, okay? So, trust me, if you do this on your calculator, okay, and I'm sure some of you will, if you take 1/2 and raise it to the 6.02 times 10 to the 23rd particle, or to the 23rd power, you will get a number, okay? Does it mean anything? No. So it's going to be such a small value. Could it happen? Theoretically, yes. Is it going to happen? No, because Mother Nature isn't going to go through that effort, okay? Because Mother Nature is going to like it where you have an even distribution of these particles. So when I walk into this room, okay, there's 1,000 things that I worry about. Well, actually, now I'm down. I have fewer reasons to worry because you all aren't in here. Actually, now I have more reasons to worry because now I'm worried about what's happening with you guys. But let's just say, I walk into this room. So one of the things I don't worry about is the room being a vacuum. So in other words, it isn't like I'm going to walk in and all of the billions upon billions upon billions of nitrogen and oxygen molecules that are bouncing around that make up the air in this room. They all didn't get together and say, hey, let's go hide in the back, okay? Let's go hide and seek. So we're going to take, so all these particles, these nitrogen and oxygen molecules, are going to go hide in the back corner of the room and then leave the rest of the room a vacuum. So I don't have to worry about when I open up the door to come into this room, okay? When I open up the door to come into this room, I don't worry about the room being a vacuum and all the particles hiding out in the back. It's not going to happen. Mother Nature doesn't like it. Mother Nature goes, it's not worth the effort. We're not going to do that. We're going to let these particles mix and mingle, and that's what's going to create an atmosphere. So pressure, your atmospheric pressure, is created by these particles bouncing around off of all of us, and that's what creates pressure. I'm not going to walk in and the room is a vacuum and they're all in the back. Maybe it could happen, probably not. So you can make the same analogy with cards, okay? So let's say that you have a deck of cards and you shuffle them, okay? So you randomly take these cards and you shuffle them. You could, when you get done shuffling the cards, it's a random shuffle, they could be in a particular order of, you could have all of the hearts, ace, deuce, 3, all the way through the king. And then you could have all the clubs, and then you could have all the diamonds and all the hearts. You could have all 4 suits in order, and it could happen. Likely to happen? Probably not. But it could happen. But it's just not very likely to happen. Okay, so with that kind of laid out, let me make this go away. All right, so when you get into the terminology of entropy, okay, so one of the key things we'll talk about is microstates. So this basically says how many different ways can this particle exist? Can it exist as a liquid? Can it exist as a solid? Can it exist as a gas? Okay? How can this thing exist? Then also, how much kinetic energy could it possibly have? Okay? Could it have, is it limited to the amount of kinetic energy that it can have, or can it exist kind of on any temperature range? So the whole key to this is that we're going to talk about entropy. So this idea of entropy, okay, right? Entropy is a measure of the disorder. So basically, the more possible ways that this thing can exist, the more potential disorder there is. So you can look at my room, for example. Unfortunately, they gave me, from an entropy standpoint, and my organizational skills, or lack of organizational skills, they gave me like one of the biggest rooms in the school. So I have a whole bunch of microstates where I can find stuff in this room, okay? I can find stuff in the cabinets over here, in the cabinets in the back. I've got 2 different storerooms. I even have access to the lab where we do the chemistry labs. I've got cabinets over there. I have so many different microstates. So what that means is that I potentially, and you all can attest to this, I have potentially a high state of disorder, okay? So when I go to look for something, it was like, where that might be. I don't know, maybe a notebook? Okay, cool. Where are my notebooks? I don't know. Are they in the cabinets? Or are they in the back of the room? Or did I leave them over there in the chemistry lab? Did I leave them at home? You know, because there's so many different places that I can lose stuff, microstates, whatever you want to call it. So I tend to have a high state of disorder. Okay, now and I see this as just by the virtue of the fact that this is one of the laws of nature. The more potential places that I can store things, the more potential there is for me to lose things. So it's just one of the laws of the universe. I'm sorry, that's just the way it goes. Now, so a process in which the disorder of the system increases tend to occur spontaneously. Okay, and that's going to be important. So again, you all have been my students. Entropy happens, disorder happens. You know, if I don't keep stuff organized, and this is one good thing that's come out of this whole coronavirus thing, is that I have had to get my Scooby snacks in a row and get organized. It's like, okay, who am I sending out to this? Who's got this, okay? But notoriously, you all can, this room. I can have this room, and look at this desk, okay? This is probably as clean as this desk has ever been for quite a while. Here's a rather embarrassing story. So this happened a year ago, last night. I was getting ready for an evening study session to get you all ready for the test. And I had a book that had all the answer keys to these problems. And I tried to stay organized. And I looked in the book, and it was a particular problem, and I could not find it. I could not find it. So I'm frantically trying to find this thing, because I really didn't want to rework this problem again, because it was a big, complex problem. And I happened to lift up some papers that were on this table. And there was that answer key. So that answer key had been on this table. Okay, this is a real life adventure. This is, I'm laying it all out there. I'm showing my vulnerability. And that answer key was still laying on this desk a year later. Okay, it was still there. After a year, I'd been gone for the summer. The cleaning crew had come in. The table had been moved around. I'd shuffled countless papers, given countless lectures from behind this table. A year later, it was still there. Okay, so my point being is that nature likes to increase the state of disorder. It increases entropy. That will occur spontaneously. Now, do not use this with your mom and dad. When you say, hey, kid, your room's a mess, pick it up. And you're going, hey, mom, dad, chill out. This is one of the laws of the universe. Entropy happens. It's just going to go to a higher state of disorder. That's how it's going to go. No, okay? And certainly don't, and if you're going to use that, do not mention my name. Do not go, Mr. Burkamp said this is just what's going to happen, and it's just going to get this way. So don't roll me under the bus, please. Don't. That is a law of the universe, but don't invoke my name on this deal. I'm in enough trouble as it is recording these lectures. I don't need more trouble. Okay, so when you talk about entropy, now this is going to be an odd thing, but you can also look at it as the ability to do work. Okay, so if you look at work as being able to exert a force through a distance. So if something's very organized, okay, you have a machine with all the parts together for it, that has the capacity to do work. If the machine is torn apart and you have a higher state of disorder, guess what? The machine can't do work. But from our perspective, what we're going to look at is the amount of disorder that's in the system. Okay, from a chemistry standpoint, we're going to focus more on the disorder side of it. So it's shown by the letter S, okay? Now, here's what's important. The units for entropy, and this will play out large later on, are in joules per mole Kelvin. Now, here's why that's important. In the back of your book, you're going to have 3 columns of thermodynamic data. Entropy, enthalpy, and Gibbs free energy. Enthalpy and Gibbs free energy are measured in kilojoules per mole. Entropy is measured in joules per mole Kelvin. Okay? So when you look at, I'm going to do some math, and we're going to use this delta H equals, or delta G equals delta H minus T delta S. Your entropy terms are in joules per mole. Okay, and you're hearing me say this again and again and again. Your entropy is in joules per mole. The other terms are in kilojoules per mole. So at some point you're going to have to make a decision. Are you going to change the 2 kilojoules into joules, or are you going to change the joules into kilojoules? And don't sit there and go, well, why don't we all have the same thing? The reason that they're not all in kilojoules is because entropy numerically tends to be a smaller number, okay? And that's why it isn't measured in kilojoules, because numerically it's just a small number, and that's why we leave it in joules. But later on, once you begin to do some calculations, listen to me, listen to me, listen to me. Make sure that you are measuring in either kilojoules or joules, I don't care, but your thermodynamic data for entropy is in joules per mole Kelvin. So, oddly enough, we're going to talk a lot about change in entropy. Now, entropy itself is tough to measure. So one of the things we don't have, like on the LabQuest, we don't have entropy probes. Okay, we don't. It would be really cool if we did, but we don't. So just like we don't have enthalpy probes either, but if you look at what happened, like when that copper sulfate dissolved in the water, we couldn't directly measure what was happening with the copper sulfate, but we looked at the impact that it had on the water around it. So when we look at the impact that it had on the water around it, and that temperature change, then we could figure out what was happening with the enthalpy of the copper sulfate. So the same thing is going to be true with entropy. We can't directly measure entropy, but what we'll do a lot is we'll talk about the change in the entropy. So we want to spend more time talking about the change in the entropy than the entropy itself. So change in entropy, just like anything you've ever done in any science class, is final minus initial, okay, or S minus S naught. Usually written final minus initial. Chemistry people like final and initial. Physics people write it as S and S naught. We're in the chemistry lecture, so we'll keep it as final minus initial. So basically, if you have a positive delta S, okay, if you have a positive delta S, that means that your final entropy is bigger than your initial entropy. Okay? So like typically, my room over a period of time is going to have a positive delta S. I'm going to have more disorder, I'm going to have more entropy at the end of the 9 weeks than I do at the beginning of the 9 weeks. Because at the beginning of the 9 weeks, oh, hey, I kind of cleaned up, I got stuff organized. And it's just going to go to a higher and higher and higher state of disorder. So typically what happens is that my room is going to have a positive delta S. Now, you can also have a negative delta S, okay? I'm going to decrease the entropy. You all look at my desk right now. There is very, very little clutter on it. So my desk now has had a negative delta S. I have decreased the entropy because of the fact that I've made everything much more organized, okay? Now, what nature likes, and this is what I said, you can't use me as an example to justify your messy room, okay? You can't sit there and go, well, this is what Mother Nature likes. Mother Nature likes a higher state of disorder, and that's true. Just don't roll me under the bus, that's all that I ask. Now, here's one of the big ideas, this one right here. What you'll see is that Mother Nature likes two things. Mother Nature likes a big fireworks show, okay, and she likes a mess. So she likes exothermic reactions, fireworks, and she likes things to be messy, to a higher state of disorder. So when I'm talking about entropy in the universe, I am talking about entropy in the universe, okay? I'm talking about big idea, entropy kind of thing. So this is where this gets a little bit philosophical, is that if you subscribe to the Big Bang Theory, and not the show, okay? This isn't like a Netflix thing, okay? If you subscribe to the Big Bang Theory, that you had pure energy, the energy cooled, you began to form atoms and hydrogen, and then the hydrogen coalesced into stars and helium, okay? And then the hydrogen formed into helium, and you were producing stars, and the stars blew up, and then that allowed the heavier elements to fuse. And this is this whole philosophical thing that we are all made of stardust. So, because all of the carbon, nitrogen, and oxygen atoms that exist within our bodies or in the universe at some point had to be formed in the death of an exploding star. That's the only way you can make these complex atoms. If that never happened, then we wouldn't be here having this discussion, okay? The universe would stop basically with hydrogen, helium, maybe a little bit of lithium, not very much at all. And so we wouldn't be here. You could not have life as we know it. So this is where, again, like I said, this discussion gets philosophical in the sense that the universe likes a higher state of disorder, but yet at some point there had to be a driving force to take those random bits of hydrogen and have them coalesce into stars to start the fusion process. So the universe is basically dark. And then all of a sudden, gravity caused enough pressure and a high enough temperature to start the fusion process. And then you saw a star blink on. Oh, great, here was the first star, okay? And then in other parts of the universe, you had that same thing happening. And so what you began to see is you began to see these stars begin to blink on, okay? So if you look at gravity being a driving force to decrease the entropy, because gravity decreases the entropy by taking these random hydrogen molecules that are floating around and pulls them together and coalesces them into stars. You start the fusion process, but then the irony of it is that, oh, well, that explodes, okay, we'll blow that up. Then you start the process over again. Then that begins to coalesce again because of gravity. So if the universe was formed without gravity, you could still have hydrogen, you could still have protons, you could still have electrons, you could still have photons. But again, we wouldn't be here having this discussion. So if gravity didn't exist within the universe, we wouldn't be here. So this is where this gets even more philosophical in terms of